Let's explore rate limiters, crucial for API stability and fairness. We'll dive into different algorithms and design considerations for robust implementations. Imagine an API that's suddenly bombarded with requests from a malicious botnet. Without a rate limiter, this surge can overwhelm your servers, causing service disruptions for legitimate users and potentially leading to significant financial losses. Rate limiters act as gatekeepers, controlling the rate at which users can access your API. We'll analyze the token bucket, leaky bucket, fixed window counter, sliding window log, and sliding window counter algorithms. Each has unique strengths and weaknesses. The token bucket algorithm is like having a bucket that holds tokens, representing available API calls. Each request consumes a token, and tokens are refilled at a constant rate. If the bucket is empty, requests are rejected, effectively limiting the rate. This algorithm is widely used due to its simplicity and effectiveness in handling burst traffic. Next, the leaky bucket algorithm processes requests at a steady outflow rate, regardless of incoming burst. Think of it as a bucket with a small hole at the bottom. Requests fill the bucket, and the water requests leaks out at a constant rate. If the bucket overflows, excess requests are dropped. This algorithm smooths out traffic, preventing sudden spikes from overloading the system. It ensures a consistent rate of processing, making it suitable for applications requiring stable performance. The fixed window counter algorithm divides time into fixed-size windows and counts requests within each window. At the start of each new window, the counter resets. If the request count exceeds the limit for the current window, further requests are rejected. This algorithm is straightforward to implement, but can be vulnerable to burst traffic at the window boundaries. Imagine a scenario where a user makes a large number of requests just before the window resets, and then immediately makes more requests after the reset. Asynchronous processing decouples request handling, preventing rate limits from impacting user experience. We'll explore how it fits into our system design. Message queues like RabbitMQ or Kafka buffer requests, ensuring they're processed even during traffic spikes. This prevents request loss under heavy load. Now let's consider caching layers. Caching rate limit counters in Redis or Memcached drastically reduces database load and improves response times. Imagine our API receives a surge of requests. The caching layer quickly checks and updates the rate limit, minimizing database interaction for each request. To efficiently manage traffic, we introduce Envoy Proxy as our intelligent gatekeeper. Envoy dynamically routes requests based on rate limits, ensuring fair access. Envoy's advanced configuration allows us to define granular rate limits tailored to specific API endpoints or user groups. This maximizes resource utilization. To track the effectiveness of our rate limiter, we integrate Prometheus for real-time metrics. Prometheus monitors request rates, error rates, and saturation levels. When rate limits are exceeded, a circuit breaker pattern prevents cascading failures. The circuit breaker temporarily blocks requests to overloaded services. Now, to intelligently manage traffic and enforce our rate limits, we'll integrate Envoy Proxy. Think of Envoy as the intelligent gatekeeper for our API. Envoy intercepts all incoming requests, checks if they comply with the defined rate limits, and then forwards them to our Backend API servers. This ensures controlled access. To gain insights into our rate limiter's performance, we'll use Prometheus. Prometheus collects metrics like request counts, rejected requests, and response times. If our rate limiter service becomes unavailable, we can implement a circuit breaker pattern. This prevents cascading failures and protects our back-end systems. To handle increased API traffic, consider horizontal scaling by deploying multiple rate limiter instances behind a load balancer. Distribute requests evenly. Consistent hashing ensures that requests from the same user are consistently routed to the same rate limiter instance, maintaining accurate counts. Implement robust monitoring to track rate limiter performance, identifying bottlenecks and potential issues before they impact users. Visualize metrics. Rate limiters are crucial for API stability. Like, share, and subscribe for more insights into system design best practices.